This video speaks about onto functions. The video will be divided to 3 parts, and the first part will speak about the definition and examples of onto functions. A function f from a set A to a set B is onto B, or it is a surjection if the range of the function f is the set B, and we write f is a function from a set A to a set B, and we write onto above the arrow. So when we say f is a function from a set A to a set B, that means A is the domain of f and B is the codomain, and so a function f is onto B if the range of the function equal to the codomain of the function. Let's illustrate the definition on the following example. Which of the following relations is an onto function? For the first one, f here, we notice that f is a function and f is not onto. This is because 2 here is not in the range of f. For the second relation g is a function and it is onto because all the elements here are in the range, so g is onto function. For the third one here, h is not a function, and this because the element here a have 2 image 2 and 4. So since a and 2 and a and 4 are in h, but 2 doesn't equal to 4. The relation I here is a function, and also I is onto since all the elements are in the range. All the elements in the codomain are in the range, so I is onto. The fourth one, j, is also a function and j is not onto, and that's because 4 is not in the range. 4 is a codomain, but it's not in the range of j. Notice that the condition of the function to be onto is a condition about the codomain. So after given the codomain, the function can be onto or not. For example, our example here, j, if we reduce the codomain to just contain 1, 2, 3, then this function will be onto. The same for the example, the first example, f. If we take 2 outside of the set and we take only the range as a codomain, then my function f will be onto. From these examples, we see that for finite relations and finite functions, it is very easy to see or to find if the function is onto. Now we move to infinite relations and infinite functions. Let us discuss the definition of onto functions using quantifiers. A function f from a set A to a set B is onto if for any element y in the codomain, which is B, I can find x in the domain, which here is A, such that y is equal to the image of x under my relation f. So f of x is equal to y. So the statement here is a universal quantifier with existential quantifier. So for any y belongs to B, I have to find x such that x and y satisfy this relation. But then a function f from a set A to a set B is not onto if the negation of these statements happens. The negation is I can find y in the codomain, which is B, such that for any x in the domain A, f of x doesn't equal to y. This means that y is not in the range of my function f. In practice, the proof of a function is onto have some working backward. So determine if a function f from a set A to a set B is onto or not. We assume an arbitrary element y in the set B, and then find a solution x of the equation y equal to f of x. F is my function, and x is a variable, and y is my assumption. I can find an element x in the domain A of my function f for my arbitrary y, then I have a proof that the function f is onto. But if I couldn't find such x for at least one value y in B, that means I get a counterexample. That means my function is not onto B. As an example, let S be a function from the interval from minus infinity to 0 to the interval from minus 4 to infinity, be defined by the formula, the image of x, and there's a function s is x squared minus 4. We want to prove that s is onto this interval. So first, working backward, I assume y is in the codomain, so y belongs to the interval from minus 4 to infinity, and I want to find x such that s of x is equal to y, but s of x by the formula is given me as x squared minus 4, and that means x squared is equal to y plus 4, and so y plus 4 is greater than equal to 0 because y is greater than equal to minus 4. So x equals minus the square root of y plus 4 is in the domain of my function. So I have for any y, I can find x in the domain satisfies this equation. So we write our proof as follows. We assume y is in the interval from minus 4 to infinity. Then y will be greater than equal to minus 4. And hence y plus 4 is non-negative. And so x is equal to minus square root of y plus 4. This will be an element in R. And with the minus, it will be in the interval from minus infinity to 0. And with this x, we have s of x is equal to s by definition of minus square root of y plus 4. And use the definition of s, it takes the square of this argument here, minus 4, and the result will be y. And hence, s is an onto function. It is very important to notice that the value of y in this interval guarantee for me that x defined by this formula is in the domain, and the verification is important to show that this formula actually gives me y. Notice that if we define another function t from the set of real numbers to the interval minus 4 to infinity by the same formula, t of x equal to x squared minus 4, the same formula as in the example above, then the proof of t is onto will be similar to the above proof. In other words, if you have an onto function and you extend the domain, the function still will be onto. The next example, we take a function f from the cross product of the integers to the integers defined by f of any pairs n and m in the domain is equal to the product of the two elements n m. We want to show that this function is onto z. Working backward, we assume q is an integer, and this q is the image of the pair nm, which by definition is equal to n multiplied with m. So we want for any q, two integers, the multiplication is equal to q. There's many solutions for two integers n and m. The product is equal to q. So I will take n is equal to the number q itself, and m is equal to 1, and then the product will be equal to q. So I have a solution. So assume q is an integer. We take n is equal to q, that means n will be an integer, and m is equal to 1, is also an integer. And so n and m, the pairs n and m, will be in the cross product of integers. And q will be the image of f of mn. That means f is an onto function. F is a function into z. We observe that for a given integer, we may have many pre-image, many numbers, pairs, which goes to this integer. For example, f of 2, 3, and f of 1, 6, and f of minus 3 and minus 2, all of them have the same image, 6. However, to prove something is onto, we need just to prove that you have at least one pre-image. So in this example, we prove that we have one pre-image by taking the number q itself and 1. This finishes the first part about onto functions.